In the previous proposition, we found an algorithm to determine if two numbers were relatively prime or not. This proposition will expand on that algorithm to find the greatest common measure of two numbers, or the greatest common factor. First, run the algorithm on a and b, which are not relatively prime. We thus have a, b, c1 equaling a minus n1b, c2 equaling b minus n2 c1, and so forth to cn, which is not 1. And cn measures cn minus 1. Or rather, cn minus 1 is equal to mn times cn. Cn is equal to cn minus 2 minus mn minus 1 times cn minus 1, which is equal to cn minus 2 minus mn minus 1 mn cn from before. Rearranging the terms shows that cn minus 2 is equal to cn plus mn minus 1 mn cn. And then factoring out cn shows cn minus 2 is equal to 1 plus mn minus 1 mn times cn, or that cn measures cn minus 2. Continuing in this manner, we'll eventually find that cn measures both a and b. It turns out that cn is also the greatest measure of a and b. To prove this, assume a different measurer exists greater than cn, say d. D measures a and b, so c1 can be written as c1 equaling ma d minus n1 mb d, which is equal to ma minus n1 mb all times d, so d measures c1. Similarly, d measures c2, c3, and so forth to cn, but d is greater than cn, so there's our contradiction, and thus cn is the greatest common measurer of a and b. Euclid includes a porism that says if a number measures two numbers, it will also measure their greatest common measure. This is apparent because the greatest common measure is made by multiplying all the common measures together. We'll finish this video with an example: 80 and 125. Subtract 80 from 125 as instructed to get 45. Subtract 45 from 80 to 35. Subtract 35 from 45 to get 10. Subtract 10 from 35 to get 5. 5 is the first number that measures its predecessor, 10, so 5 is the greatest common measure of 80 and 125.